Okay, hey Biochem. Today is Membrane Transport Day, and here are the learning objectives. So after this video, you should be able to define key vocab words. There's going to be a lot of vocab, so it's a good time for flashcards. You should be able to predict whether a molecule or ion will need a membrane transporter. Describe the types of membrane transport and the associated thermodynamics, and calculate the delta G for the transport of molecules and ions crossing biological membranes. If you don't have a calculator out, you might want to get your calculator out as you follow along to make sure that your math matches my math. All right, so we're going to start a little bit of a review of the membrane proteins that we've met so far, and then we're going to expand on our membrane proteins. So the first two sort of vocab categories of membrane proteins are just based on their location. So peripheral and integral membrane proteins are just named based on their location relative to the membrane. So the peripheral proteins are the ones that are on the outside. So this one here and this one here. And these can either be lipid linked or associated with electrostatics. Okay. And then the other type of membrane protein name based on its location is integral or transmembrane. And these are also associated via with electrostatics, but primarily with hydrophobic interactions. I'll just do interactions. Okay. From here, we have met the receptors, and then we're going to meet pores and channels. So if you'll remember, receptors are the membrane proteins, the integral membrane proteins that bind ligands and then cause an intracellular signaling cascade. Okay, so if I represent my ligand here in orange, this will be L for ligand. This is my receptor. It's an integral membrane protein. Once the ligand binds to the receptor, there are many possible pathways that could happen inside of the cell because the ligand bound to the receptor. Usually things that we talk about that go with ligands and receptors are things like KD and then also like percent activity. All right. Other types of integral membrane proteins are proteins that move things across the membranes. Okay, so then we have, in these categories, there's two main, I'll call these sort of like these ones here are our transport proteins, whereas receptors don't move anything across the membrane. Okay, so then in the transport protein category, there's two big categories. They're called either pores or channels. And pores and channels, we'll go back to... Okay, so pores allow relatively unrestricted access across the membrane. So they're very unspecific for the solute or the molecule or the ion that they let across. So they're unspecific for the solute. They're fairly unrestricted. And so the molecule or ion that's moving across, the solute that's moving across, we'll abbreviate it as S, is moving across pretty fast in comparison to other things. So I'll just make the solute a circle. So this will be my solute moving across. It's still a solute when it comes to the other side. But again, this would represent the pore, or also known as a channel. And then in contrast to that are the permeases and what are also called transporters. And these are highly specific. And highly restrictive, highly specific and restricted. Oh, I can't spell restricted. Restrict. And so these tend to also be quite a bit slower. Now there are 3 types of permease or transporters depending on how the solutes are moving across. So the first type is simply called uniport. And the pores and channels can also be uniporters. Actually, the pores and channels can only be uniporters. So a uniporter is when only one solute is moving across. The other options are where you've got 2 molecules. So we'll call this S1, and then this will be S2. If S1 and S2 move in together, this is called a symporter. And then the third type, so I'll just add symport. And then the third type is if S1 moves in one direction and S2 moves opposite of this, then that is called antiport. Okay, from here, we're going to talk more about the permease and the transporters. Okay, so there's a couple different types of the permease and the transporters. So we're going to go into that, and then we'll get into the math a bit. Okay, so the category of permeases and transporters can be further broken down into like how these solutes get across the membrane. So if it's a passive transporter, then the solute is moving in the direction of diffusion, or moving with its own diffusion, which would mean the solute is going from high concentration to low concentration. And the delta G of that, or the math of that, would mean that that transport is very favorable. The other type is when you have active transport and S is not moving with diffusion. So S is moving against diffusion, a concentration gradient. And so that would mean it's going from a low concentration to high, making the movement of that solute unfavorable or have a positive delta G. And so the active part comes in when, in order to get the movement of a solute against its concentration, it must be coupled with another process. Okay, and that leads us to the 2 other processes. So the 2 other processes, the 2 types of processes to get a solute to move against its concentration gradient are primary active and secondary active. Primary active is when the movement of the solute is coupled with ATP hydrolysis. And ATP hydrolysis has a negative delta G. I'm trying to keep I guess I was doing the math in pink. And the value of that is negative 50,000 joules per mole. Okay, so what would this look like? So if you have a solute moving, let's say it's there's my solute, and it's going to move in or needs to move in. And the concentration on the outside is 20 millimolar of solute. And on the inside, it's 100 millimolar of the solute. It's going from a lower concentration to higher concentration, which is not favorable. So if you did the delta G of transport, that little T represents transport, of the solute and calculated that out, you would get a positive value. So in order for this to be favorable, it needs to be coupled or added to another process that has a favorable delta G. And so remember that all of our thermodynamic terms are additive. So I'm literally going to add the delta G of ATP hydrolysis to this. And that should get me something that is less than 0. And so how that might be represented is on the inside or outside of the cell, this membrane protein, in addition to moving the solute across, also does a catalytic reaction to hydrolyze ATP and release the energy from that hydrolysis. And the release of the energy from hydrolysis, which will be negative, is enough to sort of pull that solute, in this case, across and into the cell. Okay, so that's primary active. So primary active means that the solute moving, the transport is coupled to ATP hydrolysis. Secondary active is the unfavorable movement of one solute is coupled with the favorable movement of a second solute. Okay, so in this, we'll do the triangle S. We'll move that one in again. Still S. We'll again make this one 20 millimolar and 100. So this S, we'll call it S1. The delta G of transport of S1, comma, S1 again is not favorable. It's moving against its concentration gradient. So this process can be coupled with a second solute, whether it's antiport or symport, it doesn't matter. I'll do a symport. A second solute, we'll call this S2, moving. Again, the direction of this one doesn't matter so much, but this one would go from high concentration, so let's say 200 millimolar to 75 millimolar. So S2 is moving down its concentration gradient, which is favorable. So I can couple the movement of S1 to the transport of S2, and that will make the process favorable, as long as the magnitude of the favorable process outweighs the other one. Okay, so that's just sort of like collecting all of our thoughts before we get started and doing some math. Okay, so just like we do in biochemistry, we like to have a quantitative thing, a quantitative piece about, in this case, it's instead of just saying, yes, it's transported, no, it's not transported, we can calculate how much energy is needed to transport ions or molecules across a membrane. So we're going to start with the most simple case with uncharged molecules, and then we'll move to charged molecules, which are also called ions. All right, so the equation goes like this. Oops, let's do this one. Okay, so delta G of transport is equal to RT ln C2 over C1, where R is the gas constant, which is 8.314 joules mole Kelvin, and T is the temperature in Kelvin, and then C2 is our final concentration. And C1 is the starting. Okay, so if I have a cell, we'll just make this the lipid bilayer of the cell, my transporter, and my solute that's moving. And I'll just say the direction of the movement here is in to the inside of the cell, and I'll make this 100 millimolar is the concentration of the solute on the outside of the cell, and the inside is 25 millimolar. Temperature, we'll say, is 310 Kelvin, and then you've got your R is set value here. Okay, so looking at this one, the arrow points, forward one. The arrow points to C2. So that will make this value C2 and this value C1. And since it's moving down its concentration gradient from high to low concentration, then I would expect when I do this calculation, I would expect a negative delta G. All right, let's do some examples. Okay, so here's an example. How much energy is needed to transport glucose from outside the membrane to inside of the membrane? So the first question is asking, like a sub-question, is this process going to be negative, positive, or zero? So it's a really good practice with these types of problems to conceptually understand whether your delta G should be negative or positive. That way you can check your math. Like you already know whether you set the equation up right or not. So when I look at this, we have glucose going from 4 millimolar to 8 millimolar, which means it's going from low concentration to high concentration. And because of that, I know that that's in an unfavorable movement. So I would expect my delta G for this to be positive. Okay, so let's calculate it out. And let's just see. So my delta G of transport for glucose is going to equal 8.314 joules mole Kelvin. My temperature is given to me up here, is 310 Kelvin, and then ln of C2 over C1. Again, the arrow points to C2, so that makes this C2, and then this is C1. 8 millimolar over 4 millimolar. You don't have to convert all the way to molar because this is just a ratio. Okay, so I already did my math ahead of time, so let's just use your calculator to see if you got the same answer as me. And I got that the delta G would equal 1786.7 joules per mole, and that makes sense to me because I said that this value should be positive. So that all checks out. Oops, I forgot to add MOL. All right, let's do an example. There's a lot of examples in this video. So how much energy would be needed to transport glucose from outside to inside? Is the process negative, positive, or zero? So here we're going from outside to inside. We're looking at 8 millimolar outside, 4 inside. This is the higher concentration, so I'm going from high to low. So I would expect this delta G to be negative. And again, we can test that. Delta G of transport of glucose, 0.314 joules mole Kelvin. Temperature is still 310. ln of C2 is 4 millimolar over C1, 8 millimolar. And I will get my value here. Also note that the units here, this Kelvin will cancel with that Kelvin, which is why our final units are joules per mole. And this is just the opposite of the other one, which is negative 1786.5 joules per mole. And that checks out because we said it should be negative and it's going with the concentration gradient. Okay, so let's make things just a little bit more challenging. What do we do if we have something that's an ion, something that is charged? So with something that is charged or an ion, we need to add in the electrical gradient. So we start, whoops, I love that highlighter. We'll start again. Delta G is R T ln C2 over C1. This is called the chemical gradient. And this describes the movement of things based on their concentration. And then if it's an ion, we add a second piece. So we're going to add in ZF delta psi. And this piece here is called the electrical gradient. So if you're moving an ion, we normally say that we're calculating the electrochemical gradient. So we add in both pieces, the charge piece and the concentration piece. Okay, so what are these added new pieces? So Z is the charge of the ion. So if our ion was Cl minus, then our Z would be -1. F is Faraday's constant, which is just another constant, 96500 joules, mole, volts. And then delta psi is the change in membrane potential. My laundry is singing. A lot of noises here today. I don't know why that's so loud and so long. Okay, so let's do just a conceptual idea of how to think about this. Okay, so I'll do my cell again and a transporter, and I will move, since we did Cl, so Cl minus, shoop, into the cell. We'll do the chemical gradient, so I'll just do another 100 millimolar, 20 millimolar. And then there's a couple added pieces to this. So you'll need to know the charges on each side of the membrane. So usually there's like a plus and a minus to indicate that there's a charge difference across the membrane. And then you'll also be told the membrane potential. And in this case, I'll just make one up. So I'll say the membrane potential is 0.025 volts. All right, so here's how we know how to set the beginning part up. So it's RT ln C2 would be 20, and then C1 is 100. And again, we're going down the concentration gradient, so I would expect this entire term here to have a negative value or be a negative delta G. And then when we add in the second part, the electrical gradient, so we'll add in the charge on the chloride is -1, so that should be a -1 there. And then you add in 96500, and then the membrane potential is the number, 0.025 volts, but we have to take into consideration the trickiest part here. Okay. We have to decide the sign on the membrane potential, or what the change in the membrane potential will be. So first, what I want you to see or to note is that we have a negative ion moving towards the negative side of the membrane. These alike charges, this negative to the negative, is not favorable. So when we calculate this out, we need to end up with a positive delta G. Right now, with the way that we have it, we have a negative times a positive times a positive, which will not give us what we want. So you can use, excuse me. So what we do is we adjust the sign on the delta psi to account for this. So I'm going to put a negative here so that now this, when we multiply it out, is now a negative value. And I'll have a negative times a positive times a negative, and that will give me the positive delta G that represents the movement of that ion and its charge to the side of the membrane that is not favorable. So in this case, you wouldn't really be able to predict the overall delta G because you would need to know the magnitude of this value and this value to know whether or not this is actually a favorable movement or an unfavorable movement. Okay, let's do some examples. Okay, so we have is the transport of potassium across this uniport spontaneous? So remember that spontaneous means negative delta G. So let's see if we can do this see if we can ballpark this without the use of a calculator. So we're going from 4 millimolar to 140 millimolar. So we're going from low to high. That's not favorable. And then we are going from a positively charged ion towards the negative part of the membrane. That is favorable. So if you were ballparking this, you would say delta G, you've got RT ln C2 C1 plus ZF delta psi. This piece we would estimate to be positive delta G, and this piece should come out to be negative delta G. So without a calculator, you can't tell. You have to actually do the math. All right, so let's actually do the math. Temperature is still 310. ln C2, again, my arrow is pointing here, so that makes this C2. And then this is my C1. Plus the charge of potassium is a +1. My membrane potential is right here, 0.05 volts. And then I need to adjust the sign on this to represent the process that is happening. So again, we said that the positive is moving towards negative and opposite charges attract. And right now I have a positive, so I'll need to make this negative so that this overall term has the negative delta G. Okay, so I calculated that ahead of time somewhere here in my notes. And I got 4338.3 joules per mole. Okay, let's do another example. Okay, how much energy to pump sodium ions across the membrane? Again, we're looking at sodium going from 12 millimolar to 145. So again, that's low to high. So I would expect that part, the chemical gradient, to not be favorable. And then the positive charge is going to the positive side of the membrane. So again, that would not be favorable. So if I'm delta G 8, not what I wanted. I wanted to do the RT ln C2 C1 ZF psi. We would say this should be positive, and then this one will also be positive. So without using a calculator, the delta G of transport for this process should be positive. So let's calculate it out and see if it is. This is my C2 because that's where the arrow is pointing. And this is my C1. The charge on sodium is +1 Faraday moles volts. The membrane potential is again 0.05 volts. And remember, I want the second term needs to overall be positive. And so I'm going to leave, that's not what I wanted, to leave this as a plus. And when I do this, my delta G of transport for sodium comes out to be 11,247.3 joules per mole. That all checks out. Okay. Let's switch things up and make things even just a little bit trickier. Okay, so we're still moving sodium out and against its, we're moving sodium against its electrical and chemical gradient. And so the question is, if we assume that the transporter is primary active, a primary active transporter, what's the maximum number of sodium ions to move out of the cell? So if you remember, primary active means that there needs to be ATP hydrolysis coupled to this process to get it to move out. We'll need to add that in. So we're going to couple the delta G of transport of sodium with the delta G of transport of ATP. And now it's not asking for the overall energy, it's asking what's the maximum number of sodium ions. And so here's where you want to add things in. We're going to use 1 ATP, and that goes out front here. And we want to know how many sodiums, and that will go out front of the delta G. And then this process needs to be less than 0 in order to get the maximum number. So essentially we're going to use all of the energy from ATP hydrolysis to pull as many sodiums across the membrane. I'm just going to scooch this up just a little bit. We've already calculated this from the previous one, so I'm not going to redo all of that math. But so X times 11,247.3 joules per mole. The delta G of ATP hydrolysis is a number, 50,000 joules per mole. I'm just going to set it equal to 0 just for now. So first you move the ATP over, so X 247.3 joules per mole equals positive 50,000. It's just... And then we'll divide by the 11,000 on both sides to solve for X. Okay, and then our units will cancel because they match tops and bottoms. And X comes out to be about 4.4 sodiums. But you can't have a decimal of a sodium. So in this case, in order to get 5 moved across, we need a little bit more than 1 ATP. And so we can't just generate energy out of thin air. So here we're going to round down to 4 sodiums. So we have enough energy to get 4 whole sodiums across. We don't have enough energy to round up to get to 5. You'd need more than 1 ATP to get 5 sodiums. In fact, you'd get more than 5. But so in this case, we're rounding down. Okay. All right. So last, more complicated math example, and then we'll end on the conceptual piece, and then that's it. Okay, so putting all of this together, so if we look at the sodium-potassium pump, and we know that there are 3 sodiums going out of the cell, 2 potassiums going into the cell, and that the movement of both of these requires the energy of ATP. Here's your membrane potentials, temperature, gas constants. Your concentrations that you need are here and here. So the overall equation, which I think is easiest to first set up. So we just want to calculate the overall delta G of this transporter. So we'll need to calculate the delta G of transport of sodium, and then we'll add that to the delta G of transport of potassium, and then we're going to add that to the delta G of ATP hydrolysis, and we will calculate the overall energy for this. And remember, there's 3 of these and 2 of these, so that goes out front. So I'm going to have, whoop, I don't know why it clicks on that one. Just go away, scooch. So I'll put a 3 out front here and a 2 out front here, and we're only going to use one of those. So let's go ahead and get this set up. Okay, let's do sodium first. Okay, so I'll have 3. Wow, why loves to, how am I clicking on that? I don't even know why it's doing that. Okay, 3, and then I'll just kind of do a bracket. Okay, so 8.314 joules, mole, Kelvin. My temperature is still 310. ln, let's see what my C2 is. So I'm moving we're moving sodium out, so that would put 145 on the outside. That's my C2, and then this is my C1. Plus, sodium has a +1. I'm going to run out of 96500 times my psi, let's see, is in millivolts. I need to convert that, 0.07 volts. And then sodium is going to the positive side, and it itself is positive. So this whole thing needs to be positive. So I'm going to leave it as that bracket. And then we'll add the potassium to that. So 2 bracket, 8.314 joules, moles, Kelvin, 310 ln. So potassium is moving inside, so the arrow is here. So this is my C2, and then my C1 is on the outside, which is 4. Potassium is also a +1 charge, 6500. And potassium is a positive charge and moving towards the negative side of the membrane. So I'm going to set this to be negative so that my entire electrical gradient term becomes negative. Bracket that in. And then I will add that to the delta G of ATP hydrolysis, which is negative 50,000 joules per mole. Whew, that's a lot. A lot of math. I got as my final answer that the process of doing all of this and using ATP hydrolysis gives me an overall delta G of negative 14,490 joules per mole as my final answer. And what this answer tells me is that I've got a little bit of energy release left over. Like, we could probably move some more sodiums and potassiums now. We haven't consumed all of the energy from the hydrolysis of ATP. Not that it's not required to use all of it, but there is a little bit of energy left over. Okay, hopefully that was enough examples to kind of get your brain going and to help you solve some other related problems. And then I just wanted to give a shout out as to, like, why are we doing this right now? How does this fit into the enzymes unit? So transporters are enzymes. So if we look at a solute moving across the membrane all by itself over here, that has a pretty high energy, a thermodynamic energy to move across. But with the use of the transporter, by keeping this solute essentially surrounded by hydrophilic things or hydrophilic atoms, the delta G of transport has a lower activation energy. And so using a transporter lowers the activation energy, which means that these are catalysts. So they make the process happen faster. So then what is able to move across without a transporter and what is able to move across with a transporter? What needs a transporter? So we can describe the movement of molecules based on their size and their charge, and that impacts their rate of diffusion across the membrane. Okay, so molecules that are small, uncharged, and hydrophobic do not need help. They will move across the membrane at a reasonable rate without any need for a transporter. Anything beyond this is going to need a transporter. Okay, so small, uncharged yet polar molecules, they'll move, but it's just really slow. So if you need to get a lot of water across a membrane, it's going to need a transporter. And then things that are large, uncharged, and polar, you're going to have a transporter for those. So this is going to need a transporter to get any of these across. And then ions, which are charged, have to have a transporter. They just do not interact favorably enough with any of the inside of the membrane to get moved across. Okay, well that ends our video, and I don't know. Have a great day. I'll see you in class. Bye.